Hello everyone, today we are going to be discussing the wave aspects of quantum particles through the lens of an experiment known as the double slit experiment. My name is Becker and let's get started. So as we know, particles on the quantum scale possess both particle and wave-like properties. This includes protons, electrons, photons, and others. With that being said, it is up to the type of experiment we do to determine which behavior the particle or wave is going to be observed. Now, the particle nature of a photon has been described by things like the photoelectric effect that shows energy comes in discrete packets. We're not going to get into the details of the photoelectric effect today, but let's discuss the wave nature of our quantum scale particles. The double slit experiment is best visualized with light waves, but its findings apply to any sort of quantum particle. So first, we need to understand the basics of waves. Diffraction is a key concept and involves the deviation of waves from straight line traveling. We can see that in this figure right here. Light is shined through a small gap of width A onto a distant screen. If diffraction were not present, as predicted by classical mechanics, then this light going through the small gap would show on an equally bright spot the same with A on the screen. We can kind of see that with this blue box right here. That also means it would be dark everywhere else, but reality shows that this is not true. It actually shows that we're going to have our brightest spot be in the middle, this little red line right here, with more diffuse lighting beyond the middle. While these two predictions are similar, the quantum mechanics is going to be what we actually see, so let's discuss it further. As long as the gap A is comparable in magnitude to the wavelength of the lights, then the plane of the slit can be considered a source of light waves. Considering that the slit is now a source, we can more easily imagine why we get diffraction on light waves compared to a single bright spot predicted by classical mechanics. As you can see here, we have our light waves just going in a straight line, the same direction as our lights. This would be classical behavior. Right here, we have our light waves kind of going at a curve, resulting from this little slit being a source of light waves. And we could see that again right here, just on a lesser angle. Now, another key basic of wave mechanics is the idea of interference. Waves are going to have crests and troughs to them that oscillate from one to the next as they travel along some sort of distance. Now, if two waves run together, then these crests and troughs are going to interact to create new sorts of patterns, also known as interference. If we imagine the crest being a sort of positive amplitude with a trough being a negative, the combination of two troughs or two crests is going to lead to an exaggerated amplitude known as constructive interference. And a great example of this is vocal harmony used by singers. Now, if we take the combination of a crest and a trough, the two will cancel out the amplitude, and this will create a sort of null amplitude, otherwise known as destructive interference. And this is the idea used by noise-canceling headphones. Okay, now let's discuss the double slit experiment. For this, we're going to test the diffraction of two sources of light from two different little slits right here, and visualize the interference between the two. So we'll make two thin slits of width A in our first wall that are separated by distance B, and then from our light source, it is going to shine through these two slits onto a screen on the other side of the wall. Now this case 1 shows what we're going to see when we only have one of our slits open, and this matches the diffraction results that we saw earlier, right here. Yeah, we can see that similar pattern. But if we open both of our slits, then we are going to see a combination of the two light waves. We get this weird pattern of extreme amplitudes, extreme maxima, and extreme minima, resulting from constructive and destructive interference respectively. It's one thing to see this, but another to see what this actually looks like, so we can see what it looks like in real life. We're going to get this nice little pattern of the brightest spot being in the middle, and then some more diffuse and more diffuse constructive interferences with some destructive interferences in between. And when we visualize this, we can see, yep, our brightest spots being in the middle of constructive interference, separated by our destructive interference. And as we go to the sides, we can see how it gets dimmer and dimmer, which is expected because the intensity of light is going to decrease as we stray away from the center. Now, while we discussed this in the context of using a light wave, the same findings will take place if we were to use a sort of electron gun as a source of electrons. If we were to use that, the particle nature of our quantum particles is more exaggerated. We still get this constructive and destructive interference pattern, but if we were to shine, say, just a handful of electrons, a low intensity, we'd be able to see more distinct points on our screen, and then after, running that enough time, using enough particles, we'll get this sort of diffuse pattern that we would expect with our light waves. So anyways, that is an explanation of the double slit experiment and why it is a way to visualize the wave nature of quantum particles like electrons or photons. This wave nature of particles is something we just don't come across when we approach systems with classical mechanics, but it is going to be very important when we approach systems using quantum mechanics. For example, it's going to be very important when we discuss particles in the context of the Schrödinger equation, when we apply that to some sort of atom, such as a hydrogen atom, and start to discuss energy levels and orbitals found in atoms. Thank you all so much for watching, and I hope you have a great day.